Good day, all participants. My name is Hota Gangarao from West Virginia University. I have Drs. Gupta and Liang with me, who will be presenting certain aspects of this module along with me. This is the second of a series of modules dealing with the fiber-reinforced polymer composites. This particular module has two parts, wherein the first half deals with durability or aging of degradation issues of polymer composites under harsh environments and incorporates the degradation rates under different environmental conditions into the design methodologies. The second part deals with the module. The second part module deals with mechanics of materials approach to find elastic properties of composite lamina, including the longitudinal, transverse, and shear moduli. Also, stress versus strain relationships of composite materials in a two-dimensional lamina are discussed. The durability part is explained by Dr. Gupta, Barry Chair, Professor of Chemical Engineering at WVU. With that, I'm going to hand this over to Dr. Gupta. Thank you, Dr. Gupta.
And I will be talking about durability of glass fiber reinforced composites. GFRPs are used in infrastructure applications such as rebars and underground storage tanks for chemicals. Once such a structure is in service, it is not easy to inspect it, but we still need to know if it will lose any properties and ultimately fail with time. We want to know when it might fail. There can be some visible signs of deterioration of a composite, and you can see that on this slide. There can be blisters or there could be discoloration. And you can see blisters in the column, and you can see the degradation and discoloration on the wrap at the bottom of the slide. So we are interested in FRP durability. What by durability we mean the material's ability to resist cracking, oxidation, chemical degradation, and other effects that come from exposure to the environment. And we're interested in this because they lead to the reduction in thermomechanical properties with time and can ultimately lead to failure. Material properties change during service. Early on, the properties can change because of what we call physical aging. The paradigm that is there in the polymers community is that processing conditions determine the structure and structure determines the properties. Since processing is done over a short time scale, the structure that results typically is not an equilibrium structure. And as time goes on, the structure tends towards equilibrium. So when a structure is formed, when we form a composite, there could be frozen-in stresses, and they are relieved with time. The polymers we use as matrices for composites are thermosets, and depending on the temperature and time of processing, the material may not be fully cured. So with time, there can be chemical reactions and there can be physical changes. These become very evident if the temperature is raised and the material is annealed. In particular, there can be free volume changes with time in glassy polymers, and this results in mechanical property changes. The structure tends towards equilibrium, and this is not a bad thing. It does not result in any deterioration in properties. This is not detrimental to composites. What is harmful is what we call chemical aging. Here, properties change due to interaction with the environment. There can be, by environment, we mean the combined effects of temperature, moisture, presence of oxygen, freeze-thaw cycles, and so on. The consequences of chemical aging are changes in properties of the matrix, changes in properties of the fiber, and changes in properties of the interface between the fibers and the matrix. And these result from oxidation, hydrolysis, and other effects that are listed on the next slide. One can examine the influence of parameters such as pH when we're talking about immersion in water, seawater, containing salt, or just plain water, influence of temperature, humidity, sustained load, freeze-thaw cycling, constant load, UV exposure, and combination of these, and the modes of deformation that we can examine properties of a composite include tension or compression, bending, and creep. Surprisingly, moisture turns out to be a very harmful agent by itself. It causes physical changes, such as lowering in the glass transition temperature, and what that does is to plasticize the matrix, and you can have significant changes, 20 degrees C change, lowering in the TG with 1 or 2% concentration of moisture in the polymer. This affects the temperature at which the composite can be used. In addition to this physical change, moisture can hydrolyze ester bonds within the matrix, particularly if you are using a polyester or a vinyl ester as the matrix, and this weakens the matrix. And this is made worse by addition of stress or an increase in temperature. The fibers can also be hurt by moisture ingress. We can have leaching of sodium or potassium oxide from the fibers. There are micro cracks, and ultimately the fiber can dissolve. And then it obviously loses its ability to bear a load. In addition, the resin, if it dissolves in the water that has gone into the matrix, it can cause osmotic pressure gradients, and this results in delamination of the fiber from the matrix. So every component of the composite can be hurt just by the presence of moisture. Our objective in understanding the durability of composites is to see what are the mechanisms of degradation, so that we can ultimately decide what safety factors we need when we design a composite for a 100-year service life. Typically, we do not have the luxury of waiting 100 years to see what might happen to a composite which is out in the atmosphere, out in the open. So we use accelerated tests and use equations such as the Arrhenius equation to correlate what we observe in the lab with what would be observed out in the field. For this, we need data on natural aging of FRPs so that we can come up with knockdown factors or safety factors. One wants reliable equations for time-dependent property changes as a function of temperature and humidity, for example. To validate these equations, there's a huge need for natural weathering data for both vinyl ester and polyurethanes so that we can predict long-term behavior. It is found that vinyl ester has better strength retention than polyester, and it is found that the mode of deformation that is very useful to examine is interlaminar shear strength, because this depends on the properties of both the matrix and the reinforcement. It is found that alkaline environments present a very damaging atmosphere, but this can be countered by the use of antioxidants, UV stabilizers, and moisture barriers. So we obtain component or coupon data in the lab, and we correlate that with field data using equations which have been proposed to represent the behavior in a long term. Creep is a manifestation of polymer viscoelasticity. This is deformation under sustained load, and this occurs even when the temperature is less than the glass, when the temperature of use is less than the glass transition temperature. There is strain that occurs, and this results in microcrack progression, interconnection of voids, softening of resin, and ultimately failure, which is a very undesirable event. If a composite is exposed to sunlight, a component of that is UV light. This can affect the polymer and result in discoloration, namely yellowing and blistering. And if the effect goes deeper, we can have chain scission and loss in properties. One finds that free radicals are formed due to the absorption of UV light in the polymer, and these free radicals can react with oxygen if it is present, giving rise to peroxides. Peroxides cause chain scission and a reduction in mechanical properties. To minimize this effect, one uses UV stabilizers, and the approach could either be physical or chemical. One can put in additives like carbon black or titanium dioxide, or one can put in UV absorbers, quenchers, and stabilizers, and there's a wide variety of these materials available, and some of these are listed on this slide. Another mode of deterioration is stress corrosion cracking. This affects amorphous polymers more than crystalline polymers, which means that the matrix in a FRP is likely to be hurt due to the occurrence of stress corrosion cracking. What one finds is that liquid, say moisture, diffuses into the polymer. It softens or plasticizes the matrix. It makes it soft, and therefore, at places where there's stress concentration, you can have creases, which then lead to cracks. And obviously, this is accelerated by an increase in temperature. Another form of deterioration is fatigue. This is failure under cyclic loads. One finds that fatigue life of FRPs is higher than that of conventional construction materials. However, fatigue life prediction is more complex in FRPs than in, say, metals, due to anisotropy of the structure and inhomogeneity of the structure. And the behavior is influenced by the kind of fibers, the orientation or architecture of the fibers, how well the composite is made, and the nature of the matrix. There are multiple ways of predicting the fatigue life, and this will be discussed next by Professor Gangarao. Thank you.
In terms of cyclic stresses, or stresses, what we call under fatigue, we define it as follows. When a structure is subjected to cyclic loading, it fails at lower magnitudes of load than its static load to failure. That load to failure under fatigue cycles in composites is higher than the fatigue stresses in metals under the same stress amplitude, which is attributed to better ductility of polymers that transfer forces from one fiber to the other when compared with metals. However, fatigue life prediction in composites is more complex due to their anisotropy than in metals, where fatigue life prediction is somewhat empirical. Obviously, fatigue life depends on fibers, matrix, and manufacturing types. Stress rises from kinks, etc. And these stress risers can lower the fatigue life. Dr. Dietenberg and I developed strain energy based fatigue life predictions for composites, and several technical papers are available in this area. I suggest that you please go over these when you get ready to design composite specimens under fatigue. The next slide deals with the strain energy based fatigue life prediction equation development. I'm not going to get into those equation developments. However, what I want to point out to you is the diamond shaped blue colored value dots are dealing with the actual experimental values, whereas the dotted green line is the strain energy based fatigue prediction curve for which we have an equation. And the red line is based on the stress related fatigue response of a composite member. Here you can see that the stress-based equations are about 4, 5, 10 times more conservative than the strain-based responses and the equations developed in relation to the practical test data that's made available. And the data that we are comparing here is based on about 500 data points under testing in bending and in tension. The next slide is dealing with the design recommendations. Herein, understanding of durability of composite structural systems under varying environments is extremely important to reasonably predict service life and incorporate these degradation factors in design by reducing the reference strength identified here as R sub 0 for a given composite material. A few of the degradation factors are shown in this slide, especially for moisture and temperature degradations. However, degradation factors are shown in the draft LRFD code for other environments such as pH, sustained loading, etc. I suggest that you refer to several technical papers on this topic that I co-authored with other researchers, and also independently, some fantastic work has been carried out and published by many other researchers across the globe. I also suggest you to refer to MIL 17 handbook, which is in the public domain. Broadly speaking, there are two degradation types to be considered in a design under fatigue. One is strength-based fatigue degradation factors. The second is the stiffness-based fatigue degradation factors. Obviously, the strength degradation factors are more severe than the stiffness factors in all loading scenarios except shear. That needs to be highlighted. In conclusion on the durability issues, I must say that understanding the durability response in terms of degradation mechanisms is critical for safe and economical field implementation. These degradation factors have already been touched upon by Dr. Gupta a few minutes earlier. Moisture attacks, including pH variation, weaken the FRP composite strength more so than the stiffness aspect of the composite, because the stiffness is a function primarily of fibers than the resin. Extreme acid environments tend to be more aggressive than extreme alkaline conditions. That is because the resin gets more affected than the fiber under acidic conditions. Alkaline conditions, however, are more detrimental for glass fiber composites than the tap water or salt water. Sustained stress tends to accelerate degradation rates and their properties under combined load and environmental conditions, as we have seen. Even though the test data is limited, we do have some data to make that observation. UV radiation degrades the matrix dominated properties more than fiber dominated properties, implying shear gets damaged more quicker due to UV radiation than tensile or bending strength. Stiffness and strength reduction factors must be used in design considerations of FRP structures by reducing the reference strength that is defined as R sub 0. The next slide deals with the characteristics of composite lamina. Here, I'm going to briefly touch base upon the kind of mechanics-based models to predict the strength of a lamina that has so much percent of volume of fiber, so much percent of volume of resin, perhaps a little bit of voids. You can see in this picture on the right bottom how the resin is getting infused, and this is the resin infusion in progress under vacuum conditions. So you can see about half the width has been infused, and as you suck the air out, create more vacuum, then you're going to see the resin progressing from left to the right. And under the mechanics of materials approaches, we have extensional modulus in fiber direction, which is along the left to right type thing in this figure, whereas the transverse direction is from bottom to the top. And these two properties, longitudinal versus transverse, are going to be somewhat different depending upon how the fabric is laid out, and it could be vastly different, or it could be nearly identical depending upon the fiber volume fraction in the longitudinal direction versus the transverse direction. I will be showing you some of the equation developments in a minute. But before I go there, I just want to say there are a couple of other theoretical approaches to determine the composite lamina properties. These are known as the theory of elasticity-based approaches, as well as the numerical evaluations based on the finite element, finite difference models. We will not be talking about those because that is beyond the scope of this presentation. Now, let me define first what is a fiber volume fraction, what is a resin volume fraction, before we figure out a very, very simple mechanics-based approaches to find the modulus in the strength in the longitudinal and the transverse directions, as well as the Poisson's effects, and shear modulus. So in this slide, the fiber and matrix volume fractions are defined as ratios of fiber volume or matrix volume to composite volume. That is why we said lowercase vf divided by lowercase v sub c, which is the composite, that is called fiber volume fraction. Whereas lowercase vm, that's the matrix, divided by v sub c, that's a composite volume. That ratio is called matrix volume. And these are identified in terms of equations 2.11, 2.12 from my textbook. I just want to keep it in line with that. So if you want to learn more about it, you can get into a lot of details in that textbook. Here, the sum of these two, VF plus VM, is the total composite volume, assuming there are no voids, 0% of voids. These fractions are computed, very importantly, to find stiffness properties, which we will see in the next couple of slides after going through these very basic concepts. Equation 2.2 in this slide, the very last equation, illustrates what I said in my previous statement. These fractions can be converted to functions of mass density fractions through basic physics, meaning multiplying it with appropriate specific gravity through basic physics, and I will not delve into that for now. The next slide talks about voids and how are they formed during manufacturing process due to improper cooling or excess moisture, bubbling of the chemicals, or even overcrowding of fibers. Similarly, resin-rich areas are possible, which lead to strength degradations. However, we are going to be assuming, as you see in my next slide, these fibers are uniformly distributed, and also the resin is uniformly coated around the fibers. But the important message here is that, as a thumb rule, if you have 1% of voids, that would reduce the strength of the composite by about 7 to 8% in the strength. So that's why you need to minimize the void. In practicality, the void percent should be around 1% or even less. Many factors play a role in void formation, including the temperature cure rate. For now, I will not go into too many details in that regard. And the volume fraction equation that I showed there from 2.10.1 to 2.10.6. Finally, the final equation, very bottom of that, is the volume fraction, where rho C theoretical is given there minus the rho actual divided by rho C theoretical gives you the volume fraction. The measurements are not easy to establish the volume fractions, but under the scanning electron microscope, we were able to measure the void content with a reasonable degree of accuracy. The next slide is a very quick example. Is a 5 kg of FRP composite with 60% fiber volume fraction, and the specific gravities of both the fiber and the matrix are 2.5 and 1.5. This is a very rudimentary example to illustrate the use of these above equations. These density or specific gravity numbers for glass and resin that I gave you here are average values, and there is a range for these values as I identified in my textbook. Now we want to find density of the composite and also mass and volume fractions. That's what I'm going to show you in my next slide. So here you can see the density of the fibers. As I told you, the specific gravity of fiber is 2.5, of a matrix is 1.5. You correspondingly multiply it with water density. In British units, that is 62.4. In the SI units, that is 1,000 kg per meter cube. Typically, glass composite specific gravity is around 2.1. And in imperial units, its density, the composite's density, I mean, is around 120 pounds per cubic foot. So that gives you an idea. And this slide deals with the development of mass fraction of fibers and matrix. Mass fractions are about 30% higher than the volume fractions. Please note that. These mass fractions that I'm dealing with correspond to, or essentially based upon, the volume fraction equation that I developed in equations 2.11 and 2.12 in the previous slides. And I will not get into the basic computations, but I'm sure you very easily follow where I'm heading from the volume fractions to the mass fractions here. This particular slide, why did I need to show these above equations? This is to derive the stiffness or modulus properties of a composite as a function of these fractions of fibers and resin. Any theoretical formulation, please note, is based on certain assumptions in any equation development. Some of the equations that we developed here are based on the following assumptions. But before I go into these assumptions, this is what is called a very simple rule of mixtures when you deal with composites. And I have already alluded to a couple of these assumptions, but I will read them out loud for you. Here, combination of fibers and matrix of constant thickness throughout the composite lamina. You will see that picture in the next slide. Fiber and matrix have perfect bond with no void. I said that in my previous slide. Elastic response is linear, meaning the Hooke's law follows. Fiber and shape distortions during manufacturing, during placement of the fibers, we are assuming they have no effect, which is, even though that's not 100% true. I already told you there will be certain formations of the kinks, and that could affect the local stress concentration effects, also the fatigue effects. The above leads to stiffness properties and Poisson's ratios of a rectangular composite of unit thickness in the longitudinal and transverse directions, including transverse shear modulus. The next slide is essentially an idealized view of fiber and matrix and their corresponding thicknesses as shown in that figure, where that particular element is subjected to longitudinal stress. The next slide, now I'm establishing an appropriate equation for Young's modulus, E value, of a composite by simple force equilibrium equation where longitudinal forces resisted by a composite of that infinitesimal element is equal to the sum of the forces resisted by the fiber and the matrix, which are given in equation 2.13.1. That's the very top equation. Key to arriving at the following equation, that's 2.14, is to note that or recognize that the strains in the composite fibers and the matrix are identical. That is a kind of an assumption. And if you use that assumption, the strains are identical in all three phases, meaning the composite, fiber, and the resin, then you get equation 2.14. Perhaps for those who forgot the definition of Poisson's ratio, I might add that it is the ratio of contraction strain in the direction perpendicular to the stress direction that is shown there in the previous slide, divided by the strain in the loading direction. Again, the derivation details in terms of the Poisson's ratio of a composite is equal to the Poisson's ratio of the fiber, which is approximately 0.2 for glass, multiplied fiber volume fraction. Add that to the Poisson's ratio of the matrix. That's why I said mu1 to m. M stands for matrix, which is in the range of about 0.3. Multiply that with volume fraction of the matrix. And this slide develops a derivation for transverse elastic modulus. To find the appropriate transverse elastic modulus of a composite, meaning the modulus perpendicular to the longitudinal modulus as given earlier, transverse stress is applied by idealizing materials as rectangular boxes as we did before, assuming axial stress in the constituents and the composite are identical and uniform, keyword, these are all assumptions, then the total extension is sum of each constituent part, which is given in equation 218. So this is what is called, to equation 218, is based upon the inverse rule of mixture. And in the similar manner, we assume the in-plane shear stress on both the fibers and matrix are identical. Shear deformation is sum of deformations of fiber and matrix to arrive at this equation number 2.20. In this example, we are using fiber volume fraction of 60%, as we did in the previous example, to illustrate the point. This implies resin volume fraction is 40%. Repeat, weight fractions are higher than volume fractions due to higher fiber density or higher fiber density than resin density or higher specific gravity of fiber than the specific gravity of the resin. For those not very familiar with the SI units, 90 GPa here in this particular example that I'm showing you is equal to 90 GPa is the elastic modulus of the fiber, whereas 4 GPa for the matrix. So 90 GPa translates to approximately 13 million PSI. That implies about 2.4 times lower modulus for the glass fiber than steel. Please note, this is the S glass fiber, not the E glass fiber. Typically, the E glass fibers have a modulus of about 10.5, 10.6 million PSI. Now, the next slide deals with the elastic modulus computations based on the rules of mixture or inverse rules of mixture, as we talked about earlier, as we derived in equations 214 and 218 respectively. The composite modulus is about 55.6 GPa. All I have done was plugged in the volume fraction of 0.6 for the fiber and fiber stiffness, which is about 90 GPa, added that to the volume fraction of the matrix, that's 0.4, multiply that with the modulus of the matrix, which is 4 GPa. So what you're finding is the longitudinal modulus that is about 55.6 GPa compared to 90 GPa for the fiber. This essentially translates to approximately 8 million, roughly speaking, 8 million PSI in the longitudinal direction, if it is a unidirectional composite. And the transverse composite is close to not quite 1.4 million PSI. So that essentially gives you a walkthrough of how to find the stiffness of a unidirectional composite. Now, I would like to now move to a much more complex topic. Let me first say what the topic is, then I'll tell you about the complexity, where this topic will be used and all that first, then I'll talk about the complexity. Now we are going to get into a more difficult concept of a lamina and a laminate. A very thin layer of a composite is commonly referred to as a lamina, and multiple layers stacked over each other is called or referred to as a laminate. How here we refer to a laminate whose thickness is very, very small. Means what? It means less than 10, the thickness should be less than 10% of the smallest dimension of a laminate in plane. And I want to show you how to establish relationship between the stress and strain of a laminate for a plane stress condition, which we call, implying that any stress variation in the thickness direction is neglected. That is called a plane stress condition. This assumption is made to reduce the complexities associated with the derivations and simplify the equations without having much loss of accuracy. Now, so you can see the various laminates, and some of these laminates may be having unidirectional fibers in the X direction. Other laminates may be having unidirectional fibers in the Y direction. There are no fibers running in this case, in this particular case, in the Z direction. But you could also have in one of these layers or lamina a 45-degree, plus minus 45-degree based fiber fabric orientation. The reason we need to have these different kinds of orientations is because in some elements of a member, we want to have high tensile strength in the longitudinal direction. In other elements of the member, we want to have fairly high shear strength in the web. That is, that element is the web, where we need fairly high shear strength, and we need high longitudinal tensile or compressive strength in the top flange and the bottom flange of a structural cross-sectional member. And that is why we need to not only have different orientations, but at the same time, we need to figure out how we are going to analyze all these under a base coordinate system. So the stress and the strain relationship under a linear elastic state of stress, undeformed of an infinitesimal element in a Cartesian coordinate system, are shown there. As you can see, here, what I want to emphasize is this slide introduces the state of stress in the three-dimensional view, and positive directions is shown with the arrow pointing away from the face of that cube. So that is the important message. So from these two very important slides, no doubt, I'm the first one to admit it's somewhat difficult for people to comprehend it the first time. But with these slides, two slides that I just showed, I'm going to now talk about how the isotropic material is different from the anisotropic material. So I'm going to start from the bottom up. Isotropic material properties are like steel and aluminum, and these properties are independent of the loading or the direction of the material axis. Whereas when I go one step further to item number 3, this is called transversely isotropic. In this, we're talking about having one symmetric plane that is isotropic, as I've shown you on the figure on my right side. So this is called, like, typically people consider timber as a transversely isotropic material. Then I complicate it further, then that is known as the orthotropic material. Fibers are oriented in 3 mutually perpendicular symmetric planes. Simplified version of this even more complex material system known as totally anisotropic system. I admit this is a difficult concept, no doubt, but please bear with me. So what I'm trying to do here is, in terms of this plane stress problem, I am trying to convert the orientation of the fibers in their local axis, meaning lamina-based axis. You see the lamina in this? I have fibers running in x1 direction. I have fibers running in 45-degree directions. I have fibers running in x2 direction. All kinds of things are happening. And I told you, from tailor making of a fabric design system, I need all these different orientations. Now the question is, how do I kind of bring all these together in terms of a I-beam or a box beam or whatever T-beam you want to call it, and bring the all properties into one global system that I showed at the extreme right. Anyway, without getting into the details, what I have shown you here is a very, very simple matrix that is dealing with variety of global stresses in local stresses. Local implying 1, 2 type, global implying x, y coordinate system. So I will not get into the mathematics, but I just want to show you that the stresses in the local coordinates are defined in the global coordinates in relation to this particular matrix, the cosine theta type matrix, sine theta type matrix that I gave you here. This is what is called a stress transformation matrix. So, and in a similar manner, we can have a strain transformation matrix, which is needed in case of problems, physical problems that we idealize as in-plane strain problems. I won't get into all the details. Here are some of the transformation matrix. If you're interested, you can go through the step-by-step derivations of this in my textbook, or there are many other textbooks that have this kind of development. The predictive composite laminar properties and stress strain models provided here give you a valuable insight into the design of composite materials. Mechanics-based approaches highlight some of the challenges we are facing with in accurately predicting the laminate properties as well as laminar properties, both in the longitudinal and transverse direction. Volume fractions and volume-based void content emerged as the crucial factors affecting the composite laminate properties. Elastic properties are examined using the rules of mixture with consideration of fiber architecture's influence on the composite. And that fiber architecture influence is transformed into a global axis utilizing what I have shown as the stress transformation matrix. And certainly, deeper understanding of the mechanics of materials and material sciences approaches are needed. The proposed method contributes to the development of durable, versatile composite materials for diverse infrastructure applications. And those diverse infrastructure applications, Dr. Liang has already shown you in the previous module. I will be talking about the design of these diverse applications in my future module presentations in a great depth. They're also available in my textbook, those designs. So with that, I thank you very much for your attention. Any questions from the audience are most welcome. Thank you.